Okay, let's get started. So, from this lecture, we start our discussion on ion transport. So that's basically another word to say we want to study the diffusion and drift. Of ions. So basically, in the sense of diffusion is, we're going to say it's driven by the change or the gradient of the concentration, while drift is basically driven by electric field. Okay. So electric field. Okay. So we're going to basically have two lectures on this. So in today's lecture, we are going to talk about so-called macroscopic picture. So this is basically saying that we are not going into the details or microscopic in details of the ions. We are not going to talk a lot about the basic mechanism of ion transport or the kind of atomistic picture. So next lecture, we are going to talk about the microscopic. So for the microscopic, we are really going to talk about vacancies into tissues, how the ions will hop from one side to the other. I mean, what kind of barrier. So, but in today's lecture, we kind of neglect a lot of details on the ion transport. We essentially say, okay, we kind of study the collective motion of ions. Okay. So then so this is what we're going to do. Okay. So we first talk about diffusion. So diffusion is kind of quite easy to understand, right? So for example, if you have this one-dimensional case, then you have the concentration. For example, here the concentration position 1 is higher than the position 2. Then there will be kind of driving force of the ions diffuse from the position 1 to position 2. It's kind of easy to understand, right? So if I further increase the gradient, so if I make it the gradient steeper, right, then of course you can imagine that there will be a larger driving force to diffuse from position 1 to position 2. It's quite straightforward, right? However, we have to be kind of quantitative, right? So we have to have a quantitative description on this. So the quantitative description of diffusion is basically Fick's law. Okay, or Fick's first law. Okay. So Fick's first law is basically saying that the J, which is flux, we're going to talk about that in a minute. Flux is kind of proportional to the negative of the gradient. Okay, so this kind of makes sense because J is basically trying to quantify how fast the ions is going to diffuse, right? So so in order to know that, you can imagine if you just pick a place, then cut into a plane which is perpendicular to the whiteboard, right? So essentially, I draw again here. Then you just choose a unit area. Then just imagine you sit here and count for 1 second how many particles or how many ions is basically going through this plane. That's basically tell you how fast the ion is going to diffuse, right? So if there are more ions pass through the plane, the diffusion is faster, right? So intuitively, J has a unit. The unit of J will be how many ions diffuse through it's going through the plane, right? So it'll be in the unit of mole. Then we have the unit area, right? So we cut a plane and we quantify that. So then the unit area is basically centimeter square. And we count that for 1 second. So then will be the second S here. So this is the unit of the flux. Okay. So then we know that for example here the flux is from position 1 to position 2, right? So definitely the ions is going to diffuse from where the concentration is high to where the concentration is low. So in this case J is positive, right? It's going to that direction. We can see that the partial C, partial X in this case is negative, right? So here the concentration is high, here the concentration is low. So the slope is negative. But there's a negative sign here, right? So then times D. D is basically diffusivity. D is diffusivity, or people call diffusion coefficient. Okay, so we can see that this guy has a unit of mole per volume, right? So because concentration is smaller per volume, then we divide that by another length because it's concentration gradient, right? That has this unit. So this times D equals J. So then we basically get the unit for diffusion coefficient or diffusivity, which is centimeter squared per second. Right? Basically, we times this with this, we get that. Okay. So it's very important to know the unit of the diffusivity of diffusion. So it has this kind of strength unit. This guy, but you will know where you get that from. Okay. So we also want to make another comment on the fixed first law. Is that fixed first law is basically kind of something kind of universal. So or make it more deep is actually from the so-called irreversible thermodynamics. I'm not going to talk about more on this, but what I want to compare is basically kind of different laws or different things that govern the transform. So what I mean, so basically, irreversible thermodynamics is saying that we have the flux, right? For example, J here is flux. Flux is something, some coefficient times the driving force. So this is flux. So this is kind of driving force. Okay. So we can see that for fixed force law. For fixed law, so the flux, the flux is basically J, okay? The driving force is basically the negative of the concentration gradient. So basically, if you apply fixed law, you have to have the concentration gradient. Once you don't have concentration gradient, then diffusion stops, right? You don't have diffusion anymore. Then the beta is basically diffusivity. So here you can see that fixed law is basically saying that you have a linear correlation between the driving force and your flux. Okay, so it's kind of make that sense. Okay, so of course J is equal to D times negative partial C times X. Or if you want to go three-dimensional, which we rarely use in this course because we kind of simplify everything into one-dimensional. I mean, if you go in three-dimensional, you have something like this. Okay. So we also want to talk about the other two things. I just want to mention them. For example, we have Ohm's law, which we will also use later, which is kind of govern the relationship between the current density. I'm going to use small j, right? So Ohm's law is basically connecting. So basically, it's quantification of how fast the current is going to flow, right? So the driving force or current density is basically electric field. E, okay. Or we know that electric field is essentially the negative of electrostatic gradient. So the phi is electrostatic potential. Phi is the electrostatic potential. Okay, so the coefficient connecting this one with that one is sigma. It's basically conductivity. Okay, so times this equals to that one. So basically that kind of makes sense because for example, a piece of metal or piece of semiconductors, the higher the conductivity, of course, the higher the current density. If you have fixed driving force, fixed electrostatic potential gradient. Okay. We can also introduce another one. It's Fourier's law. So this is for thermal transport. Or heat conduction, okay. So for heat conduction, let's see if I use F as the notation for heat flow. Okay, we know that heat flow is again is basically governed by a temperature gradient, right? So we all know that if you put one piece of materials with another piece of materials, if there's heat transfer, has to be from the one with high temperature to the one with low temperature, right? If you don't have temperature gradient, you don't have heat transfer. So we can also see that. Then, of course, there's another parameter that connecting the driving force with the heat flow, which is the thermal conductivity. So then the thermal conductivity. So we can see that the Fick's law is kind of one of the many cases where you have the linear correlation between your driving force, and the driving force is usually the gradient of something. Okay, you can see that for this is the gradient of the concentration, this is gradient of the electrostatic potential, so this is gradient of temperature. And for these laws, they are basically recognized that you have linear correlation. So essentially, if you increase this one, then the flux becomes larger. Okay. So this is basically what the Fick's first law tell you. Of course, in reality, we know that so Fick's law is kind of empirical, right? So it's called a law. It's not a. It's kind of, which means that it's basically from observation, or I mean, there's kind of assumptions or limitation to that, because the real driving force for diffusion should be, in fact, the chemical potential, right? Imagine that if you have, again, so this is the one-dimensional coordination, then you have the chemical potential difference. Of course, the species will diffuse from where you have the high chemical potential to low chemical potential, right? We know that the chemical potential can be linked to the concentration by, it should be law in A. Then can be linked to the concentration by this equation. So basically A is activity, while the gamma is activity coefficient. Okay, so there are rare cases where because the gamma can be a function of the concentration. If you change the concentration, the activity coefficient can change. So there can be rare cases that when you increase the concentration, you actually decrease the chemical potential. So there is something called acute diffusion, where you actually have the diffusion from where you have low concentration to high concentration, because the real driving force is actually the gradient of chemical potential rather than the gradient of concentration. Okay. However, you can kind of link this two, because you have the, let's say if I want to find the correlation between the chemical potential and the concentration. So because the chemical potential under standard condition is not a function of the concentration, it's fixed, it's constant. We only have this part, so then it's basically RT log A partial C. Okay. So usually what people do is write one more time, RT log A partial log C, then log C partial C. Okay. So this part is just 1 over C, right? If you take a derivative to log C, it's just 1 over C. So I'll take it here. Then we left with this part. Okay. So this is basically a measure of how non-ideal the species is, right? So this is basically, if you imagine if you have gamma equals 1, A equals to C, then this part will be 1. Okay. So this is basically measure how non-ideal the system is. So what people call it is called a thermodynamic factor. Okay. So let's use F for that. F is this guy. Okay. So of course I can write one more time. So it's partial log C times gamma partial log C. Okay, and you can break this into two terms. Basically, log C plus log gamma. So sometimes you see people write 1 plus log gamma log C. So this is basically thermodynamic factor. So this is basically F. Okay. So then that's the for the fixed first law. You can rewrite it. So J is minus D partial C partial X, right? You can kind of rewrite it to negative partial C partial mu partial X. And you have the partial mu partial C is here. So the basic D C times D RT. And you have F. F is here. Then partial mu partial X. Okay, let's write the negative sign to here. This is the flux. Okay. So as you can see, the expression is a little bit different. Okay. So now it's basically written as the gradient of the chemical potential rather than gradient of concentration. Of course, if your system is in the dilute limit, the F is equal to 1, then the whole thing is basically CD or divided by RT. Okay. Any questions? No? Okay, so of course, what we want to talk about is not diffusion itself. What we want to talk about is actually diffusion of the ions. Okay. So what's special about diffusion of ions is that ions are charged. So for example, if I have a bunch of cations, let me change a bunch of cations, each one with charge of ZE. Okay. For example, if I have magnesium, then Z is 2 plus, right? Anyway, so they're going to diffuse with flux of J. We know J is basically measured in the sense of mole per centimeter per area per second, basically measure how fast the particle is going to diffuse. But we know since they are charged particles, when they diffuse, they actually cause current, right? So so basically there's a J charge, or it's basically current. So current is basically, because we use the molar here, we say, okay, so how fast this particle diffuse will be evaluated by unit area, unit time, then per mole, okay. Then we need to convert that to charge, then we times df, okay. So F is, again, let me remind you, is Faraday constant. It's 6500 Coulomb per mole. Okay. So basically, that's the way to convert from this can be called J particle to J charge. Right, so essentially, so this is not really J, right? So this is basically, imagine that if you have a sample, imagine if you have a sample, you have more charged particle, more cations here than cations here, right? So then you have the cation diffuse that way. But when the cation is going to diffuse, then there'll be a flux of charge associated with that. We know that the flux of charge is nothing but the current, right? So we can also imagine that if they are not cations, they are electrons. Of course, each electron has one extra charge. Then the current density will be negative F, then there'll be flux of the electrons. Okay, no problem with that. Okay, so, and one final thing which we're going to use maybe later in the semester is that we just talked about the Fick's first law. We can also talk about Fick's second law. Okay. So, so if you notice here, let's see, Fick's first law is basically establishing the flux with the current force, basically the concentration gradient. The Fick's second law will have the element of time. Okay, so basically that's measuring the change of concentration with time. Okay, so how do I understand that? So we know that the Fick's first law is basically to measure the flux going through imaginary plane, right? So if I take the sample and just cut out the imaginary plane and measure how many particles going through the plane per second, so I'm going to get my flux. Okay. So let's say this is actually potential X. Okay. So let's say that so next to the plane, I got another plane just with distance of dx. Okay. So both these have the same area A. Anyway, so it can be unit area. Doesn't matter. We're going to divide that later. Then, so this would be J as the potential X. So we can imagine that there will be another J going through that plane. Okay. So B as this guy. Okay. So this two plane actually cause this actually becomes a volume, right? You can imagine I have one plane, I have another plane just next to that. But in the two planes, we actually have a volume. So the volume will be dx times A, right? Any questions? No? Anyway, okay. Yeah.
就是 G charge 那一列，后面那个 G 是
current density.
在最后面那个。
It's a particle.
G particle.
Okay. So the volume will be this guy. Okay. So let's imagine. So we have particles going into that volume and particles going out of that volume, right? So the change of the concentration times the volume should be the flux. Let's see. Basically, something going into the volume minus the particle going throughout the volume. Of course, I want to times the area of the plate, right? So if I the A can be cancelled out, then I have the particle C, particle T here should be negative. If I divide the dx to be here, let's say if I divide dx to be here, this will be just a partial J, partial X. Okay. Right, so then we have partial J, partial X plus particle C, particle T is 0. So this is basically the continuity condition. Okay, this is basically saying that so since there's no chemical reaction, so there's no particles generation or annihilation inside the volume. So the change of concentration can only be caused by the difference from the flux. Okay, so imagine the flux going inside is more than the flux going outside, then you have increase of the concentration. Otherwise, you have decrease in concentration. So I can write one more time because we know J is basically negative D partial C partial X. So if I plug this in, it will be the negative sign cancels out. Then you have another derivative. Okay, you have this one. So this is basically the most common form of fixed second law. Partial C, partial T should be the diffusivity. Then the second derivative of the second derivative to the position. Okay. So as we can see here, the concentration now is both the position and also the time. Right? If you solve for that, you're going to get the evolution of your concentration profile, because now concentration is a function of both x and t. So this is essentially a partial differential equation. PDE. Okay, so I don't know how many of you have learned how to solve for partial differential equation. I guess maybe half the class. But anyway, in this semester, we might find one or two examples to solve for that. Okay. So okay, so essentially this is a fixed second law. Okay. Another complication with the ions. So because everything I talk about here can be applied to any particles, can be applied to neutral molecules in solution, anything that can apply. But for ions, there's something quite special, right? So for ions, you have to differentiate diffusion. Diffusivity. of regular ions and defects. Okay, what does it mean? So let's take the yttrium stabilized zirconia as an example. So essentially, for this guy, we call YZ. At high temperature, you have the oxygen ion conduction, so oxygen ion can move. Okay. However, the oxygen ions cannot actually move if you have a perfect lattice. So imagine that if you have perfect lattice, let me draw a few more. So each one is oxygen ions. They cannot really move. Okay. So the only way that oxygen can move is that you create some vacancy. So let's say if you create the oxygen vacancy, or if I write in the covalent notation, these are large oxygen, right? So regular ions. Okay. So you can imagine that the only way that oxygen can move is that you have the regular ion jump to the oxygen vacancy, then you leave the oxygen vacancy here, then you keep jumping. Okay. So this is basically the way that you can have the ion transport or ion diffusion. So we'll talk more about that in the next lecture. However, here, what I want to see is that if I define, so let's see if I cut a plane here. Okay, let me show you. So let me kind of imagine a plane here, just perpendicular to this line. Okay. So let's see if I cut a plane here. Then the oxygen ion jump from here to here, right? So I, of course, can apply the fixed Paul's law, saying the flux of oxygen ions of the diffusivity of oxygen ions times the drying force, which is the gradient of the of oxygen ions, right? However, if I look at another way, so let's say if I look at the oxygen vacancies, so these are oxygen vacancies. So oxygen vacancies actually change from here to here, right? So I can also define this one. So now the concentration will be oxygen vacancies. Okay. So, I mean, you can see that if I have the oxygen ion jump from to here, the oxygen vacancy jump from here to here. In fact, how many oxygen vacancy move will have the equal amount of oxygen ions to move, right? So these two should be the same. Actually, not the same. So these two, let me write it more clearly. So this one should be negative of this one, right? So it's kind of easy to understand. However, what you so if I establish this one, I'll say the oxygen vacancy times partial C, partial gradient should be equal to the regular ions gradient. Okay. However, the problem is that the regular ions, the concentration is much larger than oxygen vacancy, right? So you can see that we have just a few of oxygen vacancies. Okay, so in fact you can establish a correlation. So this should be the fraction of oxygen vacancy times this one. So this should be something much less than 1. Right, so basically this is a fraction of how many oxygen vacancy are there for all these for all the regular ions. Okay. So if you just so if let's say if you have another ions, so if you have another oxygen vacancy created here. However, if this and jump, also jump, let's say jump twice through the plane. Okay, you know what? Let me just For the ease of understanding, let me create it here. So if I double the amount of oxygen vacancies, the flux doubles, okay, right? However, so this thing also doubles, right? So now you have 2 oxygen vacancies rather than 1, like before. However, this thing barely changes, because if you count, you still have so many of regular ions, right? So if I just plug this thing into this equation, if I ignore the sign for gauge, so what I actually get is like the ratio of the diffusivity for the defects and for ions is actually let's see. So it's actually the concentration difference is actually 1 over x oxygen vacancy. Okay. Or what I can write is the diffusivity for regular ions. So the diffusivity is a fraction of oxygen vacancy times the diffusivity for oxygen vacancy. So you can imagine that for individual oxygen vacancy, they actually jump in a certain rate, right? So this is actually kind of intrinsic. So this is intrinsic. Maybe use quotation mark or property of ions, of ionic defects, more likely. Okay, so that's why. So this is a very confusing statement. So I mean, if I say the statement is like if I increase the concentration of ionic defects, the diffusivity increases. For example, if I increase the concentration of oxygen vacancies, if I say the diffusivity increases, is this the true or false statement? Well, it's I mean it's unclear because you haven't told me what kind of diffusivity that is. Okay. So if I say if there's a diffusivity of ionic defects, then most likely the ionic defect for diffusivity, for example, this guy basically stays the same, right? So I mean, if you don't increase this too much, then no matter how many oxygen vacancies you have the same diffusivity for the defects. However, if you say, okay, the diffusivity of regular ions, for example, this guy, it actually increases. Okay. Right? Questions? No? Okay. So, is this actually so this is actually a very important detail because so if I say there's a quantitative correlation between the fraction of the defects and the diffusivity of regular ions, then you really have to think of what this does to the diffusivity. So I guess for the next lecture, we're going to say, so this actually has the this is basically linked to the kind of it's basically somewhat activated. So you know, when ion jump from the regular side to the weakened side, it has to overcome the energy barrier, right? We know that the higher temperature is, the faster the ion diffusion is. So, however, this guy can also have temperature dependence. So, but it's really case by case. For example, if I say, so this is the yttrium stabilized zirconia. So basically, you dope the yttrium into zirconium site, then you create oxygen vacancy. So this is basically charge balance. Then the amount of oxygen vacancy concentration is basically fixed by the so it's fixed by the dopant concentration. Okay. So this is the constant. So which doesn't really change. Now, if you measure the temperature dependence of this guy, there'll be only the magnesium barrier. So we'll talk about this again next week, maybe the week after. So since it's a holiday. Okay. However, if I say if I have the non-stoichiometric non-stoichiometric compound, for example, the some oxide with oxygen deficient, then the for example with Schottky pairs, or 2RT over delta. Then we know that the formation of the oxygen vacancy is also thermally activated. Okay, so then if you measure the temperature dependence of this guy, there'll be a part with the migration, and also will be a part of the thermal activation. Okay, so this you have to make a clear distinction between this one and this one. Okay. Okay, so I think it is pretty much for the diffusion. So the next thing is about drift. Okay. So drift is basically under the electric field. So essentially, if I have ions, for example, positive ions or counter ions here. So if I give it electric field this way, of course it's going to move, right? So basically on the electric field, the charged particles are going to move. Of course, we just said the drift is actually done by Ohm's law. Okay, Ohm's law basically you have the J, which is again the flux of charge. Okay, should be sigma, the conductivity, and times E. So E is basically electric field. Okay. However, we know that this guy is basically the negative of the electrostatic potential. So, for example, if I have phi at something x going like this, we know that electric field, the direction is from where you have high electrostatic potential to where you have low electrostatic potential. Then the current density is also like this. Okay. So basically, if you have linear phi at something x as shown here, then your electric field is also uniform. So it's very important that we also know what's really going to the sigma. So if you remember which we talked about last week, so we know that the conductivity is basically concentration times the ZF. Z is basically the number of charge for the particles. F is static constant. Then the M is mobility. Okay. So this is basically the drift. So we talk about drift and we talk about diffusion. Then the next is of course. So how do we combine the two? Basically, if I say all cases we have the drift and we have the diffusion in our devices, then we how to understand that? Okay. So basically, we want to understand how that ion can move under both. So let's imagine a very simple case. So let's say I have some cations with the charge of Ze, okay, positive Ze. Here in the sample in the crystal, then I have two electrodes attached to. I have positive electrode here, then negative electrode here, right? Then I start to apply voltage. Okay. So the ions can already move out from these boundaries. Okay. Can only be moved inside the crystal. Cannot really go out. Imagine what is going to happen here. So it's basically going to move to that direction, right? Then after a sufficient amount of time, so end result is that you have maybe more ions on the right compared to the left. Okay, so we can see that the drift is basically going that way because we constantly apply a potential. Okay, so basically the constant potential is fine here. Okay. However, the diffusion, so because there are more particles, more ions here than here, so of course there will be a driving force for diffusion. Okay. Right. So basically, if I imagine the driving force for drift, so that's going that way. However, for diffusion, it's going this way. Okay. So this way is going to be diffusion. So at some point, the drift and diffusion is going to cancel out. The system reaches equilibrium or reach steady state. So we want to find out what kind of condition that should be for the drift and diffusion to cancel out. So this is what we want to do. Okay. So when when we have the steady state, so the drift and diffusion cancel out mathematically. That's basically saying that the total flux is basically the flux of the drift and the flux of diffusion is basically zero. Okay. So we know that the diffusion flux is governed by the second law, first law, sorry. It's basically this one. Then the drift is basically governed by this, by Ohm's law. However, knowing Ohm's law here, so this is the current density. Or, in other words, the flux of charge rather than flux of particles, right? So we have to convert that to the flux of particles. It's basically quite easy if you divide that by Zf. So that's basically the flux of particles, right? So here is basically flux of charge. We want to convert that to the normal ions, okay? So then this is the Zf sigma minus partial phi partial x. I plug the sigma from here, the Zf mu. So again, this is not a m, it's a mu as in mobility. Then Zf partial phi partial x. Okay. So I want to combine these two. Okay. So again, let's see. Let's make some assumption. The first assumption is dilute limit. So which means f is 1. Thermodynamic factor is 1. So if that's the case, I can write one more time to be. Let's see. Where do I have that? Okay. C times D RT partial mu partial x. Okay. So this is basically nothing fancy. So we talk about that. This can be the fixed first law can be written as a function of the concentration gradient, but in fact the real driving force is the chemical potential gradient. So we derived this last class, right? So of course here f is equal to 1. Okay. All right. So another thing is like so we're going to combine this one with this one, add it together to be 0. Okay, we cannot quite get there. So another one we want, something we want to make is called a Nernst-Einstein relation. Okay. So Nernst-Einstein relation is basically tells you that under not too high driving force, so which means this guy, they are not too high, they're not too large. Then the drift and diffusion, they are pretty much the same process. Okay, so we are going to be more clear in the next lecture where we talk about the microscopic mechanism. But here we just take it for granted. So this basically gives you the direct correlation to the diffusivity and mobility. So the diffusivity and mobility is basically RT over ZF. Okay. So this is basically Nernst-Einstein relation. Okay. Of course, what you often see is also KBT over VE. So why not the case? Remember, R is KB times Avogadro constant, and F is the Avogadro constant times E. Okay. So the Avogadro constant cancels out. It can also be something like this. Okay. So let's say if I plug this in, so then from this I get a diffusivity is RT over ZF times the mobility. Okay. So then I basically plug into here, it's negative C, then the mu, then RT cancels out, I have ZF left, then partial mu, partial X. Okay. Alright, so then we are ready to write the equation. So the total flux is plus basically this plus this one. Right, so basically it's the negative C mu, sorry. Basically this term. However, I don't like this term, so what I want to write is basically C times df. Maybe let me write here. So let me times okay. Okay, so if I times the df basically at the bottom and the top, okay, this is nothing but the conductivity. Right, so if I this is already conductivity. Okay, anyway, so this is already conductivity. So let me also write a z square f square here, then this will be df5. Right, so then I say, okay, so basically I sum this one with this one. I have the common part, sigma. Then I have another part, which I can directly add together. So this is the chemical potential. So this is df5, df times the electrostatic potential, partial x. Okay. So clearly, if I say this thing is 0, so this is a constant, right? So because this is conductivity, then d square f squared. It has to be, this one is 0. Okay. So which means whatever I write here, if the gradient is 0, then the diffusion and drift cancels out. Okay. So this must be something quite important. So indeed, we define this as electrochemical potential. So this mu is electrochemical. Potential. So of course the mu is the chemical potential, and the phi is electrostatic. Okay. So this thing called tilde. So basically, this kind of curve above it, or in some case, people also use a bar above the mu. So in some literature, you also see this. So or this essentially they are pretty much the same thing in electrochemical potential. Okay, so this is very important results. So this is basically the key result that governs the transport of ions. Okay. So let me just write another time. So J total. Total means that we have the drift and diffusion. It's basically negative sigma f squared z squared, then partial mu tilde partial x. Okay. So there are a couple of things to notice. So the first thing is, so if I have drift and diffusion cancels out basically at a steady state or equilibrium, then J total should be 0, which means the equilibrium condition is the gradient of electrochemical potential is 0. Okay, of course you can break it into different parts, right? For example, in that case, if I say if I reach the place that drift and diffusion cancels out, I know for sure that this is so this is basically the constant everywhere, right? So there's no driving force for that. However, we know that the drift and the diffusion itself, the two separate terms, they are not necessarily that. For example, if I have more particles here than here, then of course I have more chemical potential here than here, right? However, that's really counterbalanced by the case that you have df phi. Okay. So again, so this thing is mu plus df phi. So basically, the electric field is this way. So that's evaluated by this electrostatic term. Okay. Now, which governs the drift. Then the diffusion is basically governed by the chemical potential. You can see that this is how to understand the case that you have drift and diffusion cancels out. Okay. So the second thing is that so this basically give you another so this basically give you a mass equation to calculate any flux under the with very simple expression you can calculate the flux or anything. Okay, if I write species I of the sigma I. No, there's no I here. Partial. Okay, I is for all species in your sample, in solids. For example, if I say I is equal to electrons, we can also use that, right? Because electron is now the electron is basically 1. Okay. However, However, for electrons, we also care about is current density. We know if the current is contributed by electron, then the direction of the current is different, is opposite to the direction of the electrons, right? So this is basically F times J electron. Then this be sigma E F partial mu delta E partial X. Okay. So basically, this is really universal, right? So this is basically saying that any charge species, if you have drift and diffusion, which means you can have both gradient of the electrostatic potential and the gradient of chemical potential, which means concentration, then this is really what you are looking for. The electrochemical potential is what we are looking for. Okay. So actually, there is a third remark I want to make. Is that for a voltmeter, if you basically take your multimeter, you measure you measure the voltage between two things. For example, if you take a battery, you take a lithium-ion battery, then you measure the voltage between the cathode and anode. If you measure voltage, what you are actually measuring for is basically this one, the delta electrochemical potential of electrons. Okay, so I'll expand on that later. Okay, so let's see how this really works out. Okay, so for example, if I have a lithium-ion battery, so for example, I have electrolyte. So I have a cathode, or you just use C. Okay, the cathode is something like lithium cobalt oxide, which is quite typical cathode. And I have anode, let's say it's graphite, carbon, I use carbon-6 to represent graphite. And I have electrolyte. So let's say I use a voltmeter to measure it, to measure the voltage. What do I get? Okay. So basically, we know that if I put a resistor here, so put a resistor here, electron is going to flow. Okay. So this is how you have a battery that can really give you electricity. However, let's say if I have the open circuit condition, so basically I put a voltmeter here. You know, voltmeter is usually means that you have a very large resistor that basically gives you the open circuit condition. So it's basically open circuit condition, and what you measure is called open circuit voltage, OCV. Okay. So then, what kind of OCV you are going to measure, right? So the OCV you are going to measure is basically governed by the difference of electrochemical potential of electrons between the two leads. Okay. So this is not electrostatic potential because you can see that these are the cathode and anode. They are made of different materials, right? So they are not in the case of the normal circuit that the cathode and anode. They are made from both of the both are the let's say copper or some metal. One thing you have lithium cobalt oxide, another thing you have the carbon or graphite. It's quite easy to imagine that the density of electrons or the concentration of electrons, or in other words, the chemical potential of electrons might be different in the two electrons. On top of that, you can have the electrostatic potential difference. Okay, so the OCV is really linked to the electrochemical potential of electrons. But let's see how that really how that the quantification really comes out. Okay, so this can be understood by solving the local equilibrium with the cathode element. So for example, let's take the this part, the cathode for a moment. Okay, so we know that the reaction for the cathode, let's say if we are discharging the so let's see if we are discharging if we discharge the battery, okay, if the negative battery to become to do electricity, it's basically we have electrolyte coming from here, the lithium from electrolyte coming from here, the electron is coming from here, going into the lithium cobalt cell. Okay. So then this is from the electrolyte. So this is coming from the cathode. So going to the charge neutral lithium into the cathode. So if I say because it's open circuit, we actually reach equilibrium for each part of the battery. Okay. So if I write the electrochemical potential of this electrochemical reaction like this, if I say let's reach equilibrium, so what I can write is basically write I can write the relationship between each potentials for each species. However, since they are charged species, basically they are ions and electrons, you have to use electrochemical potential in this case because you have diffusion and drift in the same time. Okay, then what I can write is the electrochemical potential for lithium from the electrolyte, actually for the electrolyte which is right next to the cathode, plus the electron chemical potential should be the lithium chemical potential for the cathode. Okay, so this is your cathode reaction. So you can also do the same thing to the anode. For the anode, it's basically you take a lithium out. So this is in the anode to the lithium ion into the electrode. So basically you take the lithium here, then you supply the electrons, okay? Then plus electrons, so this is anode. I mean, the same thing what you can write is you can write mu lithium anode should be the same thing as the summation of this chemical potential, the electrochemical potential. Okay. So we know that this guy is, let's say, the electrolytes are near the cathode. So this guy is near the anode. However, what I said is open circuit condition, which means that there's no net motion of the lithium ions in this case. So which means that this guy should be equal to that one because for the equilibrium condition will be there's no gradient. There's no gradient of electrochemical potential of lithium inside the electrolyte because I mean we are just holding the voltage. We are not really making the ions to move. Okay. So then that's quite encouraging because now we can cancel those two terms. Okay, so if I put this in together with that one, so what I have is basically the OCV should be the delta mu e. However, delta mu e, since we have the chemical potential here, right? So this unit should be something like kilojoule per mole. Okay, so which has the same unit as the chemical potential. So electrochemical potential essentially has the same unit as chemical potential. However, we want to convert that to voltage, basically how many volts. Right? So we have to divide by the Faraday constant. Okay. So because you can see that this guy, the unit basically is volt. Okay. Electrostatic potential, right? So how many volts you have. Okay. So this is basically F the mu E A minus mu E C. Basically the difference between your cathode and anode electrochemical potential. However, if you see this one, you will see that the mu E A minus mu E C is basically the same as the lithium. So it should be A. Lithium chemical potential. Okay, so this is also your OCV. So basically, what we get here is for electrochemical system, such as the lithium-ion battery. So at the equilibrium or at the OCV condition, so what we have is there's no net transport of lithium ions. Otherwise, you'll have the current, right? So otherwise, it won't be open circuit. Now, how do we determine the OCV? Basically have the local chemical equilibrium with the cathode and with the anode, and together we get the OCV something like this. Okay, so we can write one more time because if I again, so the net reaction is basically this thing coming from the anode to the cathode, or lithium in graphite. Graphite, maybe let's say the lithium Y carbon 6 to lithium in cobalt oxide. Okay. So you can actually define this. So you can actually define there's a reaction. So there's a reaction Gibbs free energy something like this, and you can finally write. This is basically reaction Gibbs free energy, or in this case, Gibbs free energy per mole. Okay, because it's evaluated as function of x and y. So if you change the stoichiometry, or if you change the amount of lithium in these two samples, then this mu can also change. Okay. So from this, you also get a quite familiar conclusion is that, so this has to be negative. Okay. So this has to be spontaneous. So to make the battery to work. Otherwise, it cannot really supply electricity to the outside circuit. Okay. Any questions? All right. So let's do another exercise on what this means. Then we're going to finish in this section. So another example is the solid side fuel cell. Or SOCs. Okay, so basically it has similar structure. So since it's also electrochemical anti-conversion system, so we have the, again, electrolyte. So which is usually some kind of ceramic, for example, YZ, which can conduct the, let me draw this direction, can conduct the oxygen ions at high temperature. Okay. So then in the cathode, we have the oxygen reduction. Basically, the oxygen becomes get reduced, become oxygen ions. So basically, you also have electron supply. Okay. Then the oxygen ions move to the anode to combine with something like a hydrogen to generate water and give out the electricity. Okay, so give out the electrons. Okay. So we want to do pretty much the same thing again as in the case of batteries to understand what really governs the OCV from the kind of both the local equilibrium of the electrochemical reactions and also the equilibrium condition. Okay. So first of all, the equilibrium condition. Let's see. Condition. Now it's not really the transport of lithium, it's transport the oxygen ions, but pretty much the same. In the electrolyte, the electrochemical potential gradient is 0 for the oxygen ions. Okay. Then let's see the cathode. So for the cathode, we have the reduction. Right, 4 electron. Okay, let's see. Of oxygen gas, right? So if I write that, it will be the μ2. Now the cathode plus 4 times the chemical potential of the electrons. For the cathode should be 2 times of the electrolyte. Okay, so this is cathode reaction. So for the anode reaction, we have this plus this one, get the water, let's say 2, and 4 electrons give out. Okay. So then this will be 2 times. So this will be only chemical potential because for the charge neutral gas molecules, there's not really charge. You cannot really get the electrostatic potential to do anything. So it's really chemical potential. For the anode times 2 times the electrochemical potential for the electrolyte should be 2. Mu water times 4 for the so this anode. So this is also anode. Okay. Again, your OCV should be linked to the difference basically here. So it should be F mu. Okay. So again, since we apply this one, we can really cancel out 2 terms, right? So at the open circuit condition, so this 2 should be cancelled out. This guy here and this guy here. Okay. Then what you have is if you do a little bit analysis, you have here and you move the mu c here. But remember that you have 4 because you have the stoichiometry, right? So basically you have 4. Then you have the mu2 c. Then the 2 times actually. Then plus 2. Okay. So again, so these are basically an anode. Okay. So again, so if you summarize the reaction at the cathode and reaction at anode, you have the total reaction to water. You can also define the reaction get-free energy or reaction chemical potential. So it's pretty much the same. However, because per reaction there are 4 electron transferred, so it has to be divided by 4 here. Okay. However, let's see what the reaction is really about. So let's say, so the reaction here is perhaps some kind of reaction at the standard condition and RT logarithm. So this will be another something with the concentration here. So the concentration is basically the pressure because at high temperature everything is in gas phase, right? Both the hydrogen and water and oxygen, they are in gas phase. So basically what you write is basically here, Q2, then pH2 squared. Okay. So if you plug this into this equation, okay, so let's say it's something at the standard condition and RT log pH2 square, pH square, CO2. Okay. So the first is perhaps some kind of standard potential. Okay. So which means that so if this everything is at 1 atmosphere, you get some kind of standard potential. Then you have 4 FRT log. Let's say Q. Q is basically this guy here, but with a negative sign. Basically not with the negative sign, but with the with this spot because there's a negative sign here. Okay. So basically, this is another way to say that now you can actually change the gas atmosphere, basically the partial pressure of water, hydrogen, and oxygen, which are actually changing these potentials that will cause the OCV to change, right? So this is quite easy to understand. For a fuel cell like this, if you change the partial pressure for everything, you're going to change. So if you change the partial pressure for hydrogen or partial pressure for water or the gas phase oxygen, the output output voltage is going to change. We kind of go around the circle to really break it into kind of details and also apply the condition where you have the electrochemical potential of the ions to be the same everywhere in the electrolyte. This is the OCV. However, we know that once we start flow, once we start to flow, right, then there'll be a gradient of the electrochemical potential. So this is the way it should be, right? Once we going away from the OCV, once we start to have the current, then the oxygen ions is going to flow, which means that the gradient of oxygen chemical potential the electrochemical potential of oxygen ions won't be the same everywhere. Okay. I guess that's pretty much what I want to say in this lecture. So starting from the next one, we're going to talk about the microscopic picture of the ion transport. Again, so the homework is due after the National Day holiday. So. Pay attention to that. Any questions? 有没有问题？中文问也行。没有，我们就下课。然后周四没有课，所以过年以后见。好。